In the next module, we're going to talk about the fundamentals of power. Three big components in a data center you'll hear over and over and over again: space, power, and cooling. So it's important that we get a good handle on power and understand how it works. So we're really going to take power all the way back to the fundamentals. If you have any questions while you're in the middle of this module, please use the question and comment box, and happy to answer any questions you might have. So let's get started. These are the topics we're gonna cover inside this module. We're gonna look at some of the power basics and key terms. Right? So it's important, again, that everybody has a good solid understanding of power. We don't have to be electrical engineers, but it is important to know how the power works in the data center. We're going to look at some power calculations. How do we calculate how much power a motor is going to draw, for example? Those type of calculations that come up in the data center. Give some good reference materials for that. And we're going to look at grounding. In future modules, we'll also look at power problems and some of the equipment in the data center. But we want to get a good background right now on some of the basics of power in the data center. Power is a primary resource. Again, space, power, cooling are the big three that we talk about. And when we're looking at designing a data center, power is one of those primary things we look at. Many instances of downtime are the result of power problems. So a server goes down, or an application fails, or something happens. A lot of times those are tracked back to power problems. We want to keep our power free of interruptions or distortions. Again, there's a lot of things that can go wrong with power. Your power may be very good, but depending on your utility and so on, your power may not be as good. So we rely on the equipment in a data center to keep our IT equipment free from these power problems. And our IT equipment needs to be isolated against these. So I want my server to go along its merry way without noticing any power problems at all. So let's go all the way back to the basics. Let's talk when we were kids, we're out in the backyard, we're playing with our brother and sister, and we've got a hose in the backyard, and we squirt them with the hose. Right? There's a lot of things we can look at between power and electricity that kind of correlate with each other. So a volt is equivalent to the pressure in the hose. Right? So the more and more I open up the nozzle, the more pressure I'm going to have inside that hose. So that's equivalent to a volt when we're looking at electricity. An amp is equivalent to the flow of the hose. So how much water is flowing through the hose? So obviously one of the big things that's going to impact that is how big is our hose. I can certainly get more water through a fire hose than I can through a garden hose in our backyard. Right? So we've got the pressure in the hose, we've got the flow in the hose, how much water flowing through the hose. If I were to multiply those two together, volts times amps, I get something called apparent power. So in this case, in our backyard example, this is the amount of power of water that could potentially come out of the hose, right? It's based on how wide do I open up my nozzle on my hose, and how big is my hose. Those two between them are going to control the amount of water that could potentially come out of the hose. And we call this apparent power, and I use the word potentially come out of the hose. So if I open up my nozzle a certain amount and I've got a certain size hose, I would expect to see a certain amount of water come out of that hose. But if I'm the guy that doesn't have the hose and I'm being chased by my brother with the hose, what do? I grab the hose a lot of times and I'll put a bend in that hose. I'll try to disrupt the amount of water that's coming out of that hose. So we have something called real power, and that's in watts. And this is the amount of water that actually comes out of the hose in our example, right? A certain amount of water we expect to come out of the hose based on the pressure, our voltage, or the amperage, which is our flow. But I might be impeding that by putting a crank in the hose or something like that. So we can apply these same basics to electricity. So a volt is my force of electricity that's flowing through the circuit. Think about our hose example. That's our pressure, right? Same thing with electricity. It's the force of the electricity that's flowing through a circuit. My amperes, my amps, measures the amount of current flowing. So that's my flow through the hose, right? My amount of water that's flowing through that hose. And finally, I have an ohm. This is the measure of the amount of impedance, the resistance that electricity encounters. In our hose example, this is our brother taking the hose and bending it in half and making it harder for that water to go through. So these are kind of key terms that we look at when we're talking about electricity. Some other key terms we want to look at. Alternating current, sometimes called AC power. The direction of my current constantly reverses back and forth. Right? It goes from a positive direction to a negative direction, back and forth, back and forth. The frequency at which it goes back and forth is measured in a term called a hertz. Right? This is our frequency measurement. How often is my current reversing back and forth? So that's alternating current. I can also have direct current. My current only flows in one direction. This is DC power. So we think about this when we think about batteries. Batteries provide the current just in one direction. Alternating current, AC power, the current goes back and forth. So when I look at volts and amps, right, this is my, if I remember, volts is my pressure and amps is my flow, right? Volts is my force of electricity, amps is my flow. When I multiply these two together, I get something called volt amps. Or in this case, a lot of times we'll see this in kilovolt amps or kVA, right? So if I have a voltage of 600 and amps of 96, if I were to multiply those two together, I get a kVA of 57.6 or 57,600 volt amps, okay? I could lower my voltage down to 480 volts and increase my number of amps up to 120, and I would still get 57.6 kVA. So the same amount of apparent power coming out of there. The difference is I need a bigger wire because what I've done is I've increased my number of amps. Remember, amps is the size of my hose, the size of my wire, right? So for me to have more amps, I need to carry that along a bigger wire or through a bigger hose. Let's take my voltage down to 208 volts, increase my amps up to 277. Again, I get the same amount of apparent power, 57.6 kVA. But look at the size of my wire now. It has to be 188% bigger. So higher voltage means fewer amps and smaller wires. Okay, there's a relationship between the number of amps and the size of our wires. Smaller wires, less expensive, right? Less copper that I need to buy to make that wire. So we need to start getting into our head that we would like to have smaller wires, so less amps. In order to do that, to get the same amount of apparent power, what do we have to do? We have to increase the voltage. Remember up there at the top we had 600 volts, 96 amps. Down at the bottom we had 208 volts, 277 amps to get the same amount of apparent power coming out. So how do I change between these voltages? I use something called a transformer. A step-up transformer increases my voltage. So if I want to go from 208 volts to 480 to 600, I would use a step-up transformer. And notice when I increase the voltage, I'm lowering the number of amps, right? So I can go with a smaller wire size. I can also have something called a step-down transformer. It decreases my voltage, but to carry the same amount of power, I have to increase my number of amps, okay? Would be nearly impossible to suspend a low voltage transmission wire from a pole. So as we're driving down the road and we look at those big electric wires on the side, those run at very, very, very high voltage. They have to because they need to be at lower amperage as they can. Otherwise, the wires would be very, very big and they wouldn't be able to even suspend those. Also, it's much more economical to distribute alternating current AC power using three-phase voltage sources as opposed to single-phase. And we're going to talk through what single-phase is versus three-phase. This is looking at alternating current, and this is how alternating current works. Electricity is generated by the movement of magnets. So you can see the brown magnets that are stationary, right? So you see the three brown magnets on the outside. They're in a circle. They're each separated from each other by 120 degrees, right? 360 degrees in a circle, 120 degrees between those, right? In the middle of that, we have moving magnets. And as those magnets move along, they will align with one of the magnets, right? So at this point right here, the magnets are aligning with the one in the lower left. And as we move a little bit farther, we're now aligning with the one in the lower right. And as we continue to move, it will align with the one at the top. These movement of magnets is what generates the electricity. And you see three different arrows there that are growing and shrinking in size. They grow and shrink in size based on how well those magnets are lined up with the stationary magnets on the outside. So alternating current, the direction of current flows, reverses cyclically, reverses in a sine wave. It goes back and forth, many, many times each second. In the US, they're at 60 hertz, so 60 times a second, those magnets are lining up with each other and creating the maximum amount of current, and then it'll go down to 0, and then we'll have the maximum negative amount of current. So it'll go back and forth 60 times a second. In Europe and Asia, typically it's at 50 hertz. 50 times per second those magnets are spinning around. Direct current, typically we're going to see this in telecom facilities, right? So it was always strange to me when I was growing up why when the electricity was off, our landline phones still worked. It's because these phones were being run off of DC current, big banks of batteries in the at the telecom facilities. Typically don't see direct current in US data centers. We have very heavy resistive losses over longer distances, right? So it's hard to carry large amounts of power a long distance using direct current. And we also have large conductor sizes, and that means it's expensive for us to wire in direct current. There are some instances where we'll see direct current in a data center, but it's not typically used. Almost all data center equipment is designed for AC power. Certainly this is changing a little bit. We'll talk about Facebook in one of the modules and what they're doing in their data center with a combination of AC power and DC power. But if you take a typical server that you're going to buy from someone, put it in a rack, it's got AC power plugs in the back. It doesn't have a way to input DC power into there. It's another reason why we almost always see AC power in the data centers. So we have single phase versus three phase power. Single phase, notice we've got a sine wave up there, right? Single phase, the current is still alternating. It still goes from high to low, down through 0 and back up again, right? When the AC power enters the building as a single voltage, there's two wires that come in. It's referred to as single phase. I can also have three phase power. And in this case, we get three conductors that are coming in. And you notice that instead of one sine wave, I've got three sine waves that kind of alternate with each other. They're 120 degrees out of phase with each other, right? Single phase is usually distributed to residential small commercial customers. And power enters with one or two hot wires. And we'll also have a neutral and a ground. And we're going to talk about grounding here in just a minute. Three-phase power, it's more economical to distribute because I've got smaller wire sizes. I'm really running three sections of power over the same wire, so I can use smaller wires to do that. The size of the wire is an important reason I'm using three-phase power. It's less expensive to do that. Size of the wire affects the amount of current that can pass and affects the amount of power that can be delivered. Remember, our power is volts times amps. The size of the wire impacts the amount of amps that can go over that wire. Okay, so the size of the wire ultimately impacts the amount of power that can be delivered. 120 or 240 volt versus 208 volt configurations. Residential customers, so your typical homes, are going to use single phase power, either 120 or 240 volts. When I get to a data center, I might have some single phase 120. I might also have some single phase 208 volts. I might also have three phase power going to data centers as well. right? And I could very well have a mix of these various power configurations going into my data center. So let's look at power from the utility plant all the way out to our house or our data center. Just look at how this works. So at the upper left, we've got the power generation plant. Could be coal plant, nuclear, hydroelectric, whatever it happens to be. All that mechanical energy that we generate there is all about spinning those magnets around. When I spin those magnets around, those create electricity. That electricity is carried over transmission towers. Look at the voltage, 800 kV, 800,000 volts, right? We need very, very high voltage because we want low amperage. Okay? Then we get to a regional substation, and that symbol there is for a transformer. We're going to go from 800,000 volts down to 33,000 volts. Still very high voltage. The reason we're doing that, that's a step-down transformer, right? We're stepping down the voltage from 800,000 to 33,000 is we need to be able to get the voltage down to a range where we can use that. Now 33,000 volts, still very high, so we go through a local or a building substation as our next step. And that has another step-down transformer. We're stepping down the voltage from 33,000 volts down to 480 volts. Now at that point, I can run a single phase out to our house at either 120 or 240 volts, or I can run 480 volts out, three-phase out to my building. Let's look at real versus apparent power. Big difference between these two, and same thing with our hose. Remember our hose example, our brother's chasing us around the yard, and he's got a certain amount of pressure in the hose, a certain size hose. That's their apparent power, right? The product of voltage and current, and that is expressed in voltamps. Real power is the capacity to actually do some work, and that's expressed in watts. So if I take that hose and I put a bend in it, the amount of water that comes out is going to be less. That's my real power, right? The real amount of water that's coming out of my hose. So the ratio of these two, apparent power and real power, is something called a power factor. It's a ratio of my real power over my apparent power, right? So I'm going to take my real power, divide that by my apparent power to get power factor. And that's going to be a value from 0 to 1. Sometimes expressed as a percentage. So a power factor of 0.5 would be a 50% power factor, right? This is basically telling us in our equipment how much of the power am I actually going to get out of this piece of equipment. So let's look at an example of that. So here we see a table that has 480 volts in all cases and 100 amps in all cases. So you see my apparent power, volts times amps. In this case, I'll make it in kVA, kilovolt amps. I have 48 kVA. That's my apparent power. Let's say I'm going to run that power through a piece of equipment that has a power factor of 1. That means all of my apparent power comes all the way through, right? My real power matches my apparent power when I have a power factor of 1. So if I have a power factor of 1, my real power is 48 kilowatts. Let's say my power factor, though, was only 0.9. Even though it looks like I've got 48 kVA, and I do, I only get 43.2 kilowatts out of that. I've lost some of that power to the equipment, right? Some of that power is lost. It's important to know, here's what I pay for. I pay for my apparent power. So the electric company doesn't care how I use the power. They want to know how much power I'm using from them. So I pay for 48 kVA. I'm only getting 43.2 kilowatts out of that. And look at a power factor of 0.8. I'm only getting 38.4 kilowatts out of that. 0.8, by the way, is a pretty typical power factor for a lot of UPSs. So I pay for my 48 kVA. I have a power factor of 0.8 on my UPS, and I only get 38.4 kilowatts out of that. Right? So it's important to know that when we're sizing UPSs and so on. And we'll talk more about power factor as we move through power. Let's look at a couple of power calculations. If I want to calculate watts for single phase, my number of watts is equal to volts times amps times my power factor. Right? For a three-phase, it's the same thing, volts times amps times my power factor times some strange value of 1.73. Now, where did that come from? Well, let's look at that. I have a math degree somewhere back in my background, so I like to flaunt that every once in a while, throw my math degree out there. So we'll do a little math here. Here's my single phase. I have from neutral to line 1, right? I've only got one line, it's a single phase. Okay? And let's say that that's got a value of 1. Okay? Now I turn and look at three-phase. Three-phase, I have line 1, line 2, and line 3. And whereas in single-phase, I look at the length from neutral to line 1, when I get to three-phase, I'm looking at line 1 to line 3, or line 1 to line 2, or line 2 to line 3. Now I know that line there is longer than the red line, but how long is it? Well, let's do a little math here. I know that the phase difference between line 1 and line 2 and line 3, they're all separated by 120 degrees. If I cut that in half, I have a 60-degree angle. I remember a little bit of trigonometry. I know that the sine of 60 degrees is square root of 3 over 2. And let's see, I've got 2 of those, so I've got the square root of 3, which happens to be 1.73. So when I look at three-phase power, if I want to get the number of watts, I have to take volts times amps times power factor, just like with single phase. But because I know that that line-to-line difference is bigger, I multiply that by 1.73. So if anyone ever asks where that comes from, you'll be able to tell them. When we look at a Wye connected load, and it's called a Wye connected load because if you look at the shape of it, it does come out looking like a Y, right? So the red line, the green line, and the blue line are 3 different phases, right? Phase 1, phase 2, and phase 3 that are all coming in to power the same load. So that's a Wye connected load. It's connected to all 3 phases. A couple things we need to know about a Wye connected load. My line-to-line voltage is 208 volts, right? But my phase voltage here from my line to my piece of equipment is only 120 volts. The difference is 1.73, right? So my line-to-line voltage is 208, but my phase voltage is only 120. Now that doesn't impact the current. So if I look at the current going across one of those lines, my line current is 10 amps. My phase current is also 10 amps. So my voltage, my phase voltage changes, but my phase current stays the same. Let's look at calculating motor power. So a lot of times we'll have a motor, a pump, or something like that on in our data center, and we need to calculate how much power is that pump going to draw. Right? So we've got a concept of horsepower, and the formula for this is horsepower is equal to my volts times amps times my percent efficiency of that motor times my power factor, and then I divide that by 746. And if I want to look at amps, I can just change those numbers around. If I want to know how many amps that's going to draw, I'll take my horsepower times 746 and divide by the volts and percent efficiency and power factor. Exact same thing on three-phase, except you see wherever power factor is, that PF, I'm going to multiply by 1.73, right? It's that difference between single phase and three-phase. So let's look at a real example so we can see how this would play in real life. So if I want to know how many amps will a 30 horsepower, 240 volt, three-phase pump draw, my pump has an efficiency rating of 0.95 and I have a power factor of 0.8. All I'm going to do is plug those values in, right? So my horsepower is 30. See where that is on the bottom equation there. It's 240 volts. That's where my volts go. My percent efficiency rating, 0.95. My power factor, 0.8. When I multiply all of that out, the number of amps is going to be 71. So across each phase, it's going to draw 71 amps. So if I were to put this pump into my data center, I'll know how much power it's going to draw, how many amps that's going to draw across each one of those phases. Let's look at grounding. Grounding is a safety measure. It's designed to protect us against electrical shock. And what happens is we take a ground wire, it's connected to the metal case. And we're going to explain why in a series of diagrams here. The neutral line is the only grounded circuit, and that's bonded back to the ground at the power source. Again, I think the next slide will make this a little bit more clear how exactly this is laid out. And they have different various conductor colors. It depends on what type of voltage you have and so on, so that electricians can tell which is the hot wire, which is a neutral wire, which is a ground wire, and so on. So let's look at a little electrical circuit here. So here's my source. I show that as a battery in this case. Right? That's the source of my power. I go across a hot conductor, so that's going to carry my electricity. I go through my load, and I show my load in this case in electrical terms as a resistance. That's what that dashed line is going to be, that jagged line there. And then I have a neutral conductor which carries the electricity back to ground. And by ground, we literally mean ground. An iron pipe hammered into the ground, electricity gets rid of that iron pipe, then takes that electricity, drives it into the ground. That's why it's called grounding. So let's say we got a little metal case around our load, and here's our little guy comes and he touches that metal case. Now my little guy here, and this is the extent, by the way, of my artistic talent. You're seeing it right there. Our guy is grounded by virtue of touching the ground, right? So he's okay. He can touch this ground. There's no problem with that. He's not experiencing any kind of shock there. But what were to happen if inside my load I had a loose wire and it were to touch this metal case? So you see where I've added my little wire touching the metal case? I'm okay, and here's the reason why. Electricity, like water, is going to try to find the easiest way to get to its destination, right? Water is going to find a little path that will take it downhill. Electricity tries to find the easiest way to get back to ground. So at this point, the electricity has two choices. I can go through the person to ground. Now, a person is not a very good conductor of electricity. We'll try, but we're not very good at it, right? Or the electricity can go through the metal case to the neutral conductor and back to ground. Wow, electricity says it's much easier for me to go along the ground, or that neutral conductor back to ground, than it is to go through the person. So that's the choice that the electricity will take. Let's take another example though. In this case, my electricity, my faulty wiring was before I got to the load. Well, now the electricity has a choice here. It can go through the metal case, through my person to ground, or it can go through this load and then along the wire to ground. Both of those are very difficult for the electricity to do. Both cases, they have to go through a big load. The problem is we might be the load that they choose to go through. And that's why I show my little guy with his hair standing up, right? Very good chance there that he's going to get a shock or maybe even result in death. So in order to protect against that, we use something called a ground wire. And what the ground wire does is it connects a wire from the metal case back to the ground point. So now, in this case, the electricity has really three different choices. It can go through the metal case, through my person to ground. It can go through the load along the neutral conductor back to ground, or it can go along my ground wire. Well, my ground wire is the easiest path for that electricity to take, so that's the choice that it's going to make, right? So there's a lot of things that we have to think about when we look at electricity. And in the next module, we'll talk more about some of the other power problems and so on. But it's important to get kind of a base fundamentals of volts versus amps and power factors and things like that, so that when we start talking about some of the devices, power devices in the data center, we can relate back to these power basics. If you have any questions, you can certainly ask them using the question and comment box. Thank you very much for joining us in this module. We look forward to seeing you in other modules.